Good morning, everybody. Thank you all for coming to the hardware workshop number 2. My name is Ben.
And I'm Nick.
So for today's agenda, is that coming up? Yes, it is. We'll be talking about signals, digital versus analog. We'll be talking about pulse width modulation, or shorthand PWM. We'll be talking about the remote control receiver that all of you have. An important note about pull-down resistors, and a final-ish schematic. I'll explain why it's an ish later. So to start off, let's talk about signals. Signals are everywhere. You have 4G, 5G, AM, FM radio, Wi-Fi. These are all classified as signals, right? And I'm sure you've all have heard about digital versus analog. So as a recap, analog is a continuously varying value. There's a graph on the right here that shows how signals are changing versus time. They're found in nature, like light, motion, sound, temperature, etc. An example of an analog signal being converted into electric current is the microphone. So sound waves move a microphone's diaphragm that vibrates, moving a magnet near a coil, and that generates a small current that can be amplified by an amplifier, and then goes into speakers, and then gets translated back into sound waves. In this case, the current is an analog of the change in air pressure, hence the name analog. But in digital logic, such as the ones found in computers, your smartphones, our soccer bot, these signals vary in only discrete levels, on and off. And digital circuits work using binary ones and zeros. On the graph, you can see how there's only two states, high and low. And there's a 1 and a 0, and anything in between we don't consider. Some information, though, can be lost in analog to digital conversion because we're limited to the binary system, 1 and 0, only two states. And another cool thing is you get to learn about all this stuff in ECE 2300. I don't know if you guys taken that yet, but they'll go over all this kind of stuff.
Okay. All right. For the next concept, I'm gonna talking about the pulse modulation, or in short PWM, and this is a very important concept for electronic in general, and then for our soccer ball project specifically. And it's a very simple concept. I usually think of it as pushing a gas pedal. So when you push it all the way down, you get 100% acceleration. But when you don't push down on the gas pedal, you only get you don't get any acceleration. But if you tapping it on and off at a constant rate, between 100% and 0%, then your output speed will be averaged out, and you will get an output of somewhere between that 0 and 100%. And that's an analogy. I would like to go a little bit into detail using electrical signal, which mostly what we're gonna use for our control our motors. So let's go to the overhead camera. So let's talk about DC voltage first. So DC voltage is basically voltage at a certain voltage level, and it's usually on and off. So when it's on, let's say you have a power supply of 10 volt right here, and then you're supplying it to your LED here, and then some kind of resistor to limit the current, right? And then 10 volts. So when this power supply on, you get a constant 10 volts 10 volt power supply to the LED. But when this power supply is off, then you get a constant 0 volt. So it's like the gas pedal. When you push out all the way, it's like 100%. But when you turn it off, or you don't push down that gas pedal, then it's at 0%. But what if and when it's at 100%, then your LED will be at the brightest, because the voltage supply is all the time. But what if you want to dim that LED and just have the brightness somewhere between a 0 and 100? Then that's where PW come in. And to apply, I'm gonna do a very simple PWM by, let's say, having your signal, electrical signal, in this case, be at 10 volt half of the time, and then at 0 volt half of the time, and repeatedly over multiple cycle. And this is your basic concept of PWM, 10 volt and then 0 volt. And then for 50% of the time, it's on at 10 volt, and for another 50% of time it's off at 0 volt. And in this case, you basically have a PWM signal, and it's at 50% duty cycle. So this is how you describe a PWM signal. So either the two important aspects is the duty cycle and the magnitude of the max voltage. Okay, and then the magnitude is the difference between the max voltage and the minimum voltage, which is in this case 10 volt and 0 volt. So in this case, your magnitude voltage is 10 volt. Okay, and your output voltage will be the average voltage output of your duty cycle and your magnitude. So in this case, your output voltage, because it's on half the time and off half the time, so that means the output voltage will be half of the magnitude, which is 5 volt in this case. And you can calculate using the average output voltage will equal to duty cycle multiplied by your magnitude voltage or magnitude output, which is 10 volt in this case. And another important concept in is I want to talk about is the cycles of the PWM, which mostly depends on the frequency of your microcontroller. In this case, we're using the Arduino, right? So frequency, let's say you have a frequency at 1 hertz. And what does that mean? It basically means 1 cycle per second. And 1 cycle per second. And that means that every 1 second you have 1 cycle of electrical signal repeating itself. So in this case, this will be your 1 cycle, and this will be your next cycle. And the time for each cycle is called the period. And then the frequency determine the period of your cycle. And it's, let's say your Arduino is 8 megahertz, then the time for your cycle would be 1 over 8 megahertz, and that will give you 0. What's one? It's like 1.25 microsecond for 1 cycle. And then this is your 1 cycle, and how much the signal is on and off during this cycle will determine your PWM. And then one application of the PWM signal would be your LED, your motors. So if you want your LED to be at full brightness, you have it all at 100% at the time. So basically just a full 10 volt DC signal. But let's say if you want your LED on to 75% brightness, then you just have your signal on 75 the time and off for 25 the time, and then repeat it for the next cycle. Okay? And then again, the time for each cycle depends on your frequency of your microcontroller. And the same apply for our motors. For our RC card, we just basically send these PWM signal into the driver of the motors, and that will determine the speed of your car. And how you send out these signal using Arduino, in the software you basically have a register for you to put in these value, and then it will convert these value into the PWM signals on your output. And these registers are 8 bits. So that means using 8-bit, you can have a value between 0 and 225, corresponding to 0% duty cycle and 100% duty cycle. So let's say if I want 50% duty cycle, then I can just store the value of 128 or 7 into the register of the of that output pin on the Arduino, and then that pin will output a 50% PWM signal to the output. Okay, and that's the basic concept of PWM. Next, I would like to talk about yeah, the RC receiver.
Just keep saying.
Oh, yeah. Okay. So for our RC receiver, it's a very inexpensive and simple RC receiver and transmitter, and this is called a HS06A transmitter and receiver, and it's very configurable and very simple. You basically have two input joystick on each side, and each joystick can do up and down, and then at the rest level, and then the up and down button in the middle, which we would use for speed control. Again, a PWM concept, and then the two buttons on each side will control the directions of your car, whether to move forward, backwards, or left and right. And it can communicate over a 2.4 gigahertz frequency band. And when you turn on both the transmitter and receiver, it will communicate over a wireless data link connection. And one thing to keep in mind is that these transmitter and receiver, because they're so cheap, they are not pre-bound. That means that when you turn on a receiver, whichever transmitter turn on right after that will be get paired together. So that means that let's say the transmitter from Team 18 kit can get paired with the receiver from Team 4 kit, for example. So when you go to the competition, make sure that you pair them, take turn to pair them. You turn on the receiver of one team, and then make sure that same team turn on the transmitter right after. And the control distance of this transmitter and receiver is about 60 to 50 meters. And if you look inside the receiver PCB, it's a very simple design. You basically have 6 different buttons and then one power push switch. And how it works is that when you push this joystick forward, it will press one of the buttons. If you see my mouse here, it will press one of the button, and that will send over the signal over to receiver, and then one of the output on the channel of the receiver will become 5 volt. And let's say you push the button down, and then it will press another button on here on the PCB board, and that will trigger another signal sent to the receiver, and then that another output on the channel on the receiver will become 5 volt. And then when you don't push anything, then you have a constant 0 volt on the output of that channel of the receiver. So in total, there will be 3 channels, 1 channel for the left stick, 1 channel for the right stick, and 1 channel for the up and down buttons. And each channel will have 2 different outputs, and then each of the button is pressed, one of those output will become 5 volt. So that's a simple boil down of how these transmitter and receiver work. And next, I will go over the detail of the receiver. So here you have the receiver output that I talked about in the previous slide, and you have the power outlet, which you need to power on the receiver board, and the voltage range of this receiver is between 3.6 and 6 volt. So that means that you can just use a 5 volt output, the Arduino, to power this board up, and the transmitter power the transmitter to power up, you only need 3 volt DC, and you can use a battery 1.5 volt battery for powering the transmitter. And the max load current for these receiver input is 1.2 amps, which is definitely not something you need to worry about because the maximum current that Arduino can supply is only 40 milliamp. So it's very small, so you don't need to worry too much about this max current load. And as you can see in the picture here, we have three different channels, as I said, corresponding to the right stick, the left stick, and the button on the transmitter. And the channel one here, which is the top channel, will have two different output. Each channel will have two different output, but because the transmitter and receiver that we have is very cheap, so they don't really pair. The output pairing with the transmitter button is very random. So that's why you see when you see here for example when you push the speed up button, you will have the 5 volt on the black output and of channel 1. But if you push and on channel 2, if you push the joystick up, 5 volt will appear on the red output instead. So that's something you need to keep in mind when programming your Arduino, because pushing it up doesn't mean that the red output of the channel will be 5 volt, but it depends on it's based on this configuration right here. So I will post the slide later, but if you guys want a picture of this configuration, I will send it later on the Discord channel as well. Yeah, just something, and it's very software configurable when controlling the card. So just keep it in mind, and then you should be able to control it well. Again, yeah, and then let's talk about the frequency binding method. So to turn on the remote, when you turn on the remote controller, it will flash very slowly. And then until you turn on the receiver, then it's gonna flash twice, and when you see it flash twice, that means the connection is established. Yeah, and that's pretty much for transmitter and receiver. When you actually working with it, just let me know if you guys have any question. Yeah.
One thing I forgot to mention, we forgot to add AA batteries to the kits for the remotes. So you'll have to provide that yourself. I don't know if we have budget for that, so sorry about that. That's why they're not working right now. They don't have batteries. Anyways, back to some digital logic. So as we talked about earlier, digital logic uses binary ones and zeros. For the Arduino, it uses 5 volts to represent a 1 and 0 volts to represent a 0. So imagine an Arduino with a digital input as shown here on the right. We give it 5 volts on, let's say, input A, and it interprets it as a binary 1. We give it 0 volts, and it interprets it as a binary 0. But what if we kept the pin hanging in the air? Would it be 2.5 volts, 1.3, close to 0? We don't know. And so this kind of indeterminate signal is unacceptable. That means our circuit may behave unexpectedly because we don't know what the input is. So we need to make it very clear to the Arduino if we mean a 5 volt or a 0 volt and nothing else in between. So that's when we get into the concept of pull up and pull down resistors. So they're used to bias the inputs of a digital circuit to stop them from floating about randomly when there is no clear input. So circled in red is an example of a pull up resistor. So the point of this is to ensure that when the input is not connected to anything, that it's going to be by default at 5 volts. We have the resistor there to limit the current because we don't want to send all the available current into that pin. We don't want to short it out. Actually, when the switch closes, we don't want to short the lowercase a side straight to 5 volts. That's bad, bad, bad. So a pull-up resistor, as it implies, pulls it up to 5 volts or whatever rail you're using. A pull down is the same case, except the resistors are connected to ground, so that if you leave the pin hanging, it's gonna stick to ground. And for the case of your soccer bot, we provided 1K resistors to pull down the input. So when the remote control is not on or when it's unplugged, the inputs for the Arduino are just going to sit at 0. And here's a website link at the bottom if you want to learn more about pull up and pull down resistors. So this is the final-ish schematic. I say ish because it's actually open to you guys. If you want to add more features to this, you can. This is the base schematic just to provide the basic functionality of SoccerBot. But there are plenty of extra, there are almost plenty. There's a few extra digital pins in there. It's these red ones right here. These ones can be used for anything you want. More LEDs, sensors, whichever. So hopefully everyone has a schematic. I'm sorry, my printer doesn't do color, so it doesn't have this nice color here to illustrate the different wires, but we'll be assembling that today. None of the code has been, or we haven't provided the code yet, so we can't test the schematic just yet. But for today, let's just build it, get it ready for our next workshop, which is software 1. So let me get the overhead camera going here. Any questions, by the way, before we get started? No? Let us know if you're missing any parts. We have lots of spares up here. Oh, another thing, we'll be assembling the chassis as well. So we're going to put all the parts onto the chassis. It should basically be done by the end of today, so that by the next time we come back, we can load all the software onto it and it should run. I'm different. Okay. Are we gonna? Oh yeah, let's do that first. Actually, I gotta grab the bolts. Yeah, you got it. So we'll start off by mounting the motors into our chassis. Also, I want to thank Chris Live for printing these in our school colors. I think they're pretty cool. It's like this reflective goldish color. So make sure you have all 4 motors, all 4 yellow gearboxes. And then look for in your bag these long-ish bolts. I think there are 2 kinds of bolts in here. You want the longer one. So these right here. And you want 8 of those, 2 per motor. And we have 4 motors. So we'll just do like that. And then in addition to those 8 bolts, you want 8 accompanying nuts. Yeah. So here are my 8 bolts. I will get my 8 nuts out of here, roughly. Probably 8.
What's the shorter?
The shorter one? I think it's for this guy.
Yeah,
this guy. Alright, so once you've located all your required parts, go ahead and look at your chassis real quick and make sure there are no supporting material inside this cavity and also the ones on these sides here. Want to make sure all that's cleared out so we can slide in the motor. Okay, once you've verified that, let's bolt in our first motor. So grab a gearbox, like this one, and I would suggest pointing the wires outward so they can wrap around to the top because that's where they'll be going. And slide them in such that the white axle points outward and slides through here, just like that. And once they're seated fully in, you should be able to see a hole here going through, and that's where you can send in your bolts. It doesn't matter which side you send it through, just as long as it's secured well. Oh, mine broke off. Okay, I'm going to use this side. Oh, that broke again. Uh, oh man, I gotta grab a different one. Okay, small problem. I think the clearance on these is not as forgiving as we had thought. It seems the only one of them seems to line up well. The other one, is your guys' like that too? Okay. In that case, we'll just be mounting one bolt per motor, which should be okay. It's on this side, so this part might fly off, but that should be okay, I think. So if that lines up, just send a bolt through there, and it should come out the other side, just like that. And in your bag of parts, I believe the remote controller came with a screwdriver, so you could use that to secure it in. It should be this black one right here. Alright, yeah, that one works. So, grab a nut and hold it in place, then screw it in. Something that should help put the bolts in is actually your screwdriver. It's the perfect diameter to fit through the hole. So if your screwdriver can go through all the way, then that should clear the way for your bolts. Just like that. All right, hopefully everyone has gotten their motors into their chassis. It should look like this in the end with all four installed. We didn't do all 4 bolts or all 8 bolts just because ours didn't quite line up, but it's okay with just 1 bolt. So, going back to the breadboard from last workshop, you can go ahead and remove most of the wires, because we'll be doing things a little differently this time. So I will remove probably just the ones for the LED, probably the LED entirely just because I don't want it to get in the way. And I think your receivers should be disconnected. So let's connect them up now. So remember from last workshop, the right side of this breadboard is our 5-volt line. This receiver can only take up to 6 volts, so make sure to not connect it to the left side, as that is our 12-volt rail. We want to connect it to our 5-volt rail. So to do that, look at the black and red colors, and connect it to the header or the bus, like so. And then for this large connector, the way we have it connected is, so I wish these were numbered, but they're not. Take your connector and make sure that the red wire is facing the USB connector of your Arduino, and connect that first red wire to A0 on the board. So that'll be the fourth pin from the USB connector. So that connect that to A4 at A0. Hopefully my camera focuses. There we go. So have it start out at A0 and it should end at A5. Just like that. And on the schematic, that will be your A0 to A5. This is where we connected the motor driver. And we'll worry about these pull downs a little bit later. So
I'm gonna post the schematic in the content channel, so
okay.
that just in case
Yeah, sure. Okay.
yeah, let me just make a quick announcement.
Sure. All right.
Guys, if you want to have a look at the schematic separately, I post a PDF on the Soccer Block content channel, so it's easier that way if you got it to one follow on there.
One thing that I forgot to do is connect my 12-volt line. So on the left side, I'm going to take ground. It doesn't matter where I put it. I'll just put it here. And I'll take a plus and put it here. And I'm going to take this red 12-volt line and connect it to VN. Very important to connect the left side to the VN pin. This is carrying 12 volts and only 12 volts. And then again, just to recap from last workshop, this orange wire, or whichever wire you've used, is your 5-volt line, which connects to the right side of the breadboard. And then the ground, we want to bridge them together as we want them to both have the same ground reference. So I'm going to bridge it over like so. So both blue lines are joined together by this black wire. So that's the Arduino and the receiver. Now let's get the rest of the components wired up. So I need some more jumper wires. Wires? Okay.
He has like one extra wire in there. Or as in, because right now I have VN and then ground.
All right. So let's move on with connecting the rest of the circuit together. So on your board, so far we've connected the analog ins, which go to the receiver for the controller. So here's just my board for reference here. The wide connector goes on the right side starting at A0. And then the digital side is clear for me at the moment. So I'll start connecting that together. So let's start with the motor driver. I'm going to grab some short leads for this. So the first thing that I want to do is connect the motor driver's power. We want to power the driver so that it has power to operate. So I'm going to take a red lead, and I'll need the other schematic. Oh, it's the same one. Okay. So as you remembered from last workshop, these motor drivers are not symmetrical. They do have an orientation. So on your motor driver, you should see a little notch at the top right here. And that indicates the top of the chip. And on your schematic, the notch should be here. So
I think we should face it the other way in this case. It's more
oh,
intuitive
okay.
for them.
Do a lot of people have theirs the other way?
Yeah.
Oh, okay. Hang on just a sec. I need to rotate mine. Okay. Did they have it like here?
Yeah.
Okay.
So, like that.
All right. All right, scratch that. This is my new board now. The notch should be facing outward, away from the Arduino. So there's the notch right there. And on the schematic, this is where that notch would be. So if you have it like this, you're looking at it straight on. Each pin should correspond with what we have labeled on the schematic. Oh, this one fell out. Oops. Okay. All right, so let's start with connecting the 5 volts to the motor driver. This is to bring power to the driver. So that would be on the schematic the plus V, or pin 16, or in this case, the top right corner of the chip. So we take our lead, connect it to that row, and then this is our 5 volt line. Remember, the right side is 5 volt, the left side is 12 volt, so we connect it to the 5 volt side, just like that. Then of course we need to ground our chip. So the ground pins, we actually have 4 on the driver. It's these 2 here and these 2 here. It doesn't matter which one you use, they're all tied together. So for my case, I'm just going to use the one on the right. So that would be either the 4th or 5th pin down from the 5 volt pin. So I'm going to count 1, 2, 3, 4, just like that. And that's our ground pin. So there should be 2 spaces between the red wire and the black wire. And then the black wire goes to the ground on the 5 volt side. And now let's start working on the enable pins. So let me get rid of the schematic as that's the wrong one. I'm going to draw this notch again here. So on this schematic, our enable one, which is pin 1 on the driver, controls the left motor speed. So we'll take a wire and connect it to the top left corner, which is the one right here. And if you see on the circuit diagram, our left speed is right here. And that left speed goes to D6 on the Arduino. So we take the wire we just connected, go to the Arduino, and look for D6, which is right here. D6. That's our D6 right there. Next, I'm going to cross these out as I work on them. So we got left speed. Now we want to do left backward. When this pin is high, it's going to drive the motors backwards. So we want to connect it in 1, which is pin 2, which is right below enable 1, which is what we just plugged in. So take your extra lead and connect it to the row right underneath enable. So there should be 2 right next to each other. And if we look at the schematic, left backward goes to pin D3. And on the board, that would be D3 right there. So we just connect D3, just like that. The next one we want to do on this side is left forward, which goes to in 2, which is the second to last pin on the left side. So I'm going to grab a different color here. Oops, that's what broken. Okay, so that was the second to last, so it'll be this one right here. And if we see left forward goes to pin D4, which is right above D3, so that should be easy to locate. I should say right below D3. So that's D4, the green line goes to D4. And then another important line that we need to connect is the power that goes to our motors. This is the power or the current that gets redirected through the chip into the motors. So remember that we have 2 powers going into our chip. One to power the actual chip, and the other one so that we can power our motors, since they're 2 different voltages. So the power for the chip is right here, the one we connected first. And the power for the motors is the one that's at the bottom left corner. Right there. This is my red wire. And on the schematic, that's V motor. And as we can see, V motor connects to the battery and also V in of the Arduino. So on the breadboard, this junction would be the entire left column of our breadboard. So we take the red line and connect it to the right side. And I forgot to connect my battery, but my battery would go here. And recall from last workshop, your battery leads should look like this, where they're oriented vertically. If you have them connected horizontally as such, that would short out the plus and minus, which could cause some damage to your board. So make sure that your battery connectors are oriented vertically as such. So that completes the left side of the driver. Just going to cross it out. So now we need to work on the right side. It's basically the same thing, just going to different digital pins on the Arduino. So let's start with backward right. We've already got this one connected, so I'm just going to cross that out. in 4, which is backward right, would go to D7 on our Arduino. So in 4 is the second one from the top right. Just like that. And this line would go to backward right to D7 on your breadboard, sorry, on your Arduino. So there's D7. There. This line right here is D7. Next is forward right, which is in 3, the second to last on the right side. So D3, sorry, in 3 would be second to last, right here. This is the one that I disconnected, second to last. And that lead would go to forward right, which is D8. So on my Arduino, that would be this one right here, which is D8. And lastly, we need to connect right speed, which is the bottom right pin. Always remember where your chip is oriented. I like to keep mine facing forward all the time. So we'll take the green lead and connect it to the bottom right. And right speed would go to D5, which is the last pin that's not occupied right there. So we're going to take this wire and shove it in the middle there, like so. And if you did it right, there should be no gaps in any of these pins, and they should be starting at D3 and going all the way to D8, as you see here on the schematic. So that's everything you need to do for the motor driver. Now we need to work on the pull-down pins that I mentioned earlier. So in your kits, there should be 6 1K resistors. It's a little bit hard to see, but they're the ones that are colored black and brown. As a reference, here are the 220 ohms that we use for the resistor. This one's a little bit clearer. It's really hard to see because red and brown is pretty close, but the one on the top is our 220 ohm. Those go to our LEDs, which is not what we need right now, so you can ignore those. And they only came in 4s, so if you have a pack of 6, you know that's the right one. So again, the color ordering for this one should be brown, brown, black, black, then brown, if you're reading it from this orientation. And these are all 1Ks. So, to connect them to your board, I recommend bending them into this staple shape. And to connect them, we take one lead of the resistor and connect it to the first pin on the receiver of the remote control receiver and connect the other end to the ground. And then we just repeat this for all pins to ground.
It's routed. It's from there. I don't think it's kind of.
Oh, okay. Gotcha. So we have 6 of these leads to connect. So grab all 6 of your resistors and connect them to the receiver. So I have 3 so far, I have 3 more to go. It's getting kind of tight here. Okay, so here's all 6 pull down resistors connected. One thing to note is that we don't want any of these leads here to be touching each other. Since these are independent signals, we want them to have their own independent paths to the Arduino. If they're bridging, it's okay, nothing's gonna fry, but if you wanted one signal to only go, or so you only wanted one signal to be active, it may turn on a different signal, which might activate some other thing. So let's say you're trying to go right, it could go forward, it could go backward and forward at the same time. So just make sure that all these pins are isolated and just away from each other. It's okay if these ones touch on this side of the resistor because they're all connected to the same ground, so that side doesn't matter. It's just the side that's on the Arduino that must be isolated. If it helps, you could put some like pieces of paper in between or like tape or something to isolate them. But just keep in mind, if your soccer bot is acting strange, it might just be because they're touching on these leads here. Now for the LED, we have about 4 minutes left before the next class comes in. So I will push that to the next workshop. Unfortunately, I don't think we have enough time to get it onto the chassis yet. So we'll save that for next workshop. But for now, that should complete the majority of the circuit of SoccerBot. All that's left from this point on is to connect the LEDs and the 4 motors to the Arduino. And for your chassis, just hang on to them. Keep them safe as it's a little bit fragile. And of course, hang on to this battery bucket as well. Thanks for watching, and I hope you learned something. And if you have any questions, let us know in the Discord. We are always accessible, and good luck.